Well, thank you so much for having me. So I'm talking about what is at least superficially an even simpler subject, namely just ordinary fluid dynamics. But fluid dynamics in the context of what I think is an unusually clean system that can be probed in a lot of detail. So the system in question is the unitary Fermi gas. I'll remind you in just a second what that is, but maybe just a small slide of how I got into this game. So personally, my background is really more in nuclear and particle physics. So at the time, I was actually trying to understand transport in a more complicated system like the quark-gluon plasma or the dilute neutron fluid that, for example, appears in neutron star mergers. And so the unitary Fermi gas seemed like a very clean model system to study a number of questions that we encountered. It's also a beautiful system to study kind of fluid dynamics on the edge, by which I mean fluid dynamics in unusually small systems, systems that are unusually strongly driven, systems that you're trying to probe on very short time scales or very short length scales where it's not immediately obvious that something like fluid dynamics should be appropriate. And then one reason I'm still giving these talks is indeed that there's some bit impressive progress in experimental control. So the original experiments were, oh, there was some kind of harmonic trap, and then the only thing you could really do is turn the trap off and watch it expand. But by now there are these beautiful potentials where you can put it in a box, and then there's an external drive, and you can probe it locally, you can measure the temperature locally. So there's been a lot of progress in just experimentally probing the system. So, oops. Oh, it's just slow. I went too fast. So I apologize for those who know this well, but let me just sort of at a very simple level repeat what the unitary Fermi gas is. So imagine you have a very, very dilute gas of just spin-1/2 particles, and it's so dilute that you can think of the interaction as just some kind of square well potential. Then if you have an attractive square well, then the scattering length is negative, but there need not be a bound state if the potential is shallow. If you make it deeper, of course, eventually a bound state will appear. That's the moment where the scattering length goes to infinity. And then eventually, of course, the scattering length will change sign. And now we're taking this formal limit where I keep the bound state exactly at threshold, but I decrease the range of the potential. So I don't know, this may be, no, it works, okay? So I keep the bound state exactly at threshold, but I reduce the range of the potential, making it deeper and deeper, so that the bound state stays at threshold. And that's a beautiful system because it's clearly very strongly correlated. The scattering length is infinite, but all dimensional parameters that characterize the system are either 0 or infinite. So this is just a scale invariant system, has no parameters at all, but it's clearly a strongly correlated system. And there are all sorts of universal relations already at the two-body level. For example, the scattering amplitude is just purely 1/ik if you're at the universal point. Okay. So to me, the way I think about it is, again, a sort of hierarchy of effective field theories. Ultimately, of course, the real system is, lithium or potassium, something fairly complicated. But the system is so dilute that you can think of it as just some non-relativistic field theory of spin-1/2 fermions. And again, they just interact by a single contact interaction with the single coupling strength, and that strength is not a parameter because you tuned it to unitarity, whatever that means in your regularization scheme. If you go to sufficiently high temperatures, this actually just is a classical gas because that T matrix goes as 1/k. If you sit at sufficiently high temperature, that actually is a weakly interacting system. It has ordinary quasi-particles, just atoms, and they're described by a Boltzmann equation with the very, very simple scattering term because it's just S-wave interactions. And as you go to sufficiently long distance, at any temperature, we believe that ultimately fluid dynamics will emerge. And of course, fluid dynamics is some kind of effective field theory, meaning the frequency and the momenta at which you probe the system cannot be arbitrarily large. And within fluid dynamics, what controls this is that we want to make sure that dissipative corrections are not 100%, and that means that the frequency range is ultimately controlled by the ratio of something like viscosity to the ordinary pressure in the system. So the parameter is something like viscosity divided by entropy density that controls this expansion. So this is something after the previous talk, I don't even have to say, except to say that in my talk, there actually is energy conservation. So this, in the normal phase of the unitary Fermi gas, is just an ordinary fluid, like water. And so the conservation laws are just mass, energy, and momentum. And so now we want to write down the corresponding currents. So we want to take the constitutive equations and expand them into gradients. So you encounter this usual building block, which is just gradients of the velocity. And then at leading order, the stress tensor has an ideal part, just pressure and density, and it has viscous corrections that come from shear viscosity and bulk viscosity. And in principle, you can push this further and write down terms with two gradients and so on. So there's a gradient expansion. And the same for the energy current. It has an ideal part, which is just enthalpy, and then there are corrections to the viscosity and to thermal conductivity. And again, you can try to write down higher order terms. Now this, as I mentioned, is a scale invariant fluid, so the fluid dynamics actually simplifies a little bit. In particular, there's a universal equation of state. There's a complicated equation of state, pressure as a function of density, but there is a very simple one just given by scale invariance, which is pressure as a function of energy density, and that's just a coefficient 2/3. So the 2, if you wish, is a reflection of non-relativistic scale invariance. If this was a relativistic fluid, this would be a 1/3. So that's what we get in the heavy ions. And in the viscous term, the main simplification is that this is a scale invariant fluid, so there is no bulk viscosity in the system, and that indeed has been experimentally checked. Okay? Sometimes we would also like to do linear response. So as a theorist, I still try to think of ways in which one could implement. So this is the linear response to an actual gravitational wave that goes through your fluid. That's usually too weak to actually see anything, but again, in the cold atom systems, at least in principle, we have a chance to engineer something like this, and we're still pondering as to how you might do this. So in principle, you can couple a dynamical metric to this system and see how, for example, the stresses in the system would respond to a time dependence of that background field. This kind of formalism, of course, is also useful to just derive things like the Kubo relation. So for example, you can think of a simple linearized perturbation. There will be a response to that. So there's the stresses induced by that strain. And this response function has a very simple linear expansion. Again, fluid dynamics is a gradient expansion. So the ideal piece is just the pressure, and the first non-ideal correction is viscosity. And that, of course, is just an ordinary Kubo relation. And then this formula, again, is to show that for this to be a gradient expansion, we want eta omega to be less than pressure. I think I'm pushing the wrong button. So as I already mentioned, in this fluid at high temperature, there is a kinetic description in terms of ordinary quasi-particles. So the densities in the system can just be written as moments of a particle distribution function. So the particle density, the momentum density, and the stresses, and they just solve a regular Boltzmann equation. Here again, I made it kind of needlessly complicated. So this is what it would look like if you actually couple to an external metric. But the collision term is very simple, just S-wave collisions. So you can apply the regular Chapman-Enskog kind of expansion. So we shear the fluid, and we compute the viscosity and the thermal conductivity. This is a scale invariant fluid, so just based on scale invariance, the shear viscosity has to scale as temperature to the 3/2, but the coefficient in front will then be a pure number that in principle you can compute from kinetic theory. And the same with the thermal conductivity. So in this fluid, the Prandtl ratio, so thermal conductivity over specific heat times viscosity is just 2/3 at high temperature, just like an ordinary gas. The system, by the way, is sufficiently simple that I can actually go ahead and compute even second-order hydrodynamic coefficients. I can compute something like the shear viscous relaxation time in this fluid. Actually, a very simple result that the shear viscous relaxation time is just viscosity divided by pressure. Okay. What's also nice about this fluid that at least in principle, I can map this kinetic theory onto an ordinary quantum field theory. So I can compute the kinetic results for the viscosity as a high temperature expansion in field theory, where I can identify the kind of Feynman diagrams that have to be resummed to give ordinary kinetic theory. So in this case, the Feynman diagrams that you have to sum into the Kubo formula are known, and there's essentially 3 classes of diagrams that have to be summed, where this wiggly line, so it's meant to be a correlation function of the stress tensor, so the wiggly line meant to be 2 external stresses. The solid lines are just the fermions, and the dashed lines are pair propagators, so I resummed all the 2-particle scatterings. So these diagrams can actually be computed. Actually matching onto the hydrodynamic limit is still a little subtle because there is a non-commutativity of limits as usual, that the limit of frequency goes to 0 and density of the gas goes to 0, don't commute. So there's some subtlety, but I can compute the leading corrections to viscosity, and then you can compare if there's a difference. I mean, once you can reproduce the high temperature limit, you go to low and lower temperature. In that case, this, non-relativistic field theory becomes non-perturbative, but I can just take these diagrams and compute them anyway, even if I don't have a controlled expansion anymore. And it's actually remarkably smooth. So this is viscosity as a function of temperature. The red curve is the Boltzmann expectation, and the blue dots is a numerical calculation done by Ensign-Sperger of these diagrams. And it sort of extrapolates remarkably smoothly all the way down to TC. So at least according to this, we expect this extrapolation into the sort of deeply quantum regime to be smooth. And this is what the spectral functions look like. So it's very Drude at high temperature and then more complicated at low temperature. Final thing I wanted to say about kind of basic theory is that what I find also interesting is that we can compute the kind of short time limit of the response function. So in principle, you can take the Feynman diagrams and compute at very small frequency. That's very hard labor to resum all these diagrams and look at the small frequency limit. But you can study the small frequency limit just by an operator product expansion. So, the eta of omega, so the viscosity is a function of frequency, just defined by a correlation function. And if I compute the correlation function at very short time, that's high frequency, I can just ask what operators can possibly contribute in the operator product expansion. And the leading 2-body operator that can contribute is something that's known as the contact in the unitary Fermi gas community. So it's just a 4-particle operator. It's, if you wish, just a local density of pairs. And so the short time limit or the high frequency limit of viscosity is governed by that operator, and then you can immediately read off what the frequency dependence must be on just dimensional grounds. And so this will go as 1/square root of frequency. So there's some interesting non-analytic behavior. This actual expectation value is something that, again, is a non-perturbative thing. You have to measure it. But again, it's something that people are interested in for other reasons anyway. So that number actually is known. Okay, so talk a little bit about experiments. Again, historically, the figure that sort of captured my interest was the one on the left. So that's the original kinds of experiments that were done about 15 years ago. So you have a gas that's confined in an ellipsoidal trap. Indeed, the scale on these figures doesn't change. They're all on the same scale. And then the trap is turned off and the gas starts to expand. But because the gas is behaving hydrodynamically, it's expanding predominantly sideways because the pressure gradients in that trap, this is a short direction and a long direction. So in hydrostatic equilibrium, the pressure gradients in the short direction must be much bigger. And so the gas then explodes predominantly sideways. And that's a hallmark of fluid dynamic behavior because if the atoms didn't interact, they would just expand isotropically. And so that is clearly not seen. What's seen is fluid dynamic behavior. And indeed, in this plot, so this is expansion time, and these are the two radii, so this is the short radius and the large radius, and the solid lines are just ideal fluid dynamics, no viscosity at all. And you see that's already an almost perfect fit, that this looks like almost ideal expansion. Indeed, what viscosity will try to do is viscosity will try to equalize the velocities in the expansion, and since the long axis isn't expanding very much, viscosity wants to increase the expansion in the longitudinal direction and decrease in the transverse, and you can try to read it off from these experiments. So the initial experiments weren't quite accurate enough to do this, but nowadays they're more accurate experiments, and in principle, the analysis is very straightforward. There is an experiment and it measures this aspect ratio as a function of time during the expansion and as a function of, say, the initial temperature or the initial energy of the cloud. And that should be enough information to then reconstruct what, say, viscosity is as a function of density and temperature. The two difficulties, one difficulty is that, the density in the cloud is obviously not constant, so you somehow have to unfold. That's tedious, but in principle, it's of course doable. There is a more serious problem which troubled us for a long time, and that's of course that the system is not a fluid everywhere. It's relatively dense in the center, strongly correlated in the center, but then it becomes very dilute in the outer corona of this system. And in that outer corona, obviously, eventually the mean free path will be much bigger than the size of the system. So it's certainly not a fluid in this dilute corona, it's just a fluid in the center. And you might imagine that maybe that doesn't matter very much, that you just sort of run fluid dynamics and there are not that many particles in the corona anyway, so even if you make a mistake there, that maybe it doesn't matter much. That unfortunately is not the case, and for the following reason. If you compute the amount of viscous heating that's going on in a system like this, viscous heating is proportional to viscosity and gradients of the fluid velocity squared. Now, the expansion profile is essentially a kind of Hubble flow, so the velocity increases linearly from the center of the cloud. So gradients of the velocity are approximately constant in space. They depend on time. And viscosity, of course, is a function of density. As a result, will be a function of position. And it's a good fluid in the center, so viscosity will be small in the center. And then viscosity will grow as you go further out. And indeed, in a very dilute fluid, viscosity is not dependent on density at all, just depends on temperature. So if the system is at some temperature, viscosity, at least in principle, the viscosity that you compute in kinetic theory tends to a constant, even though the density becomes arbitrarily small. And so if you just naively apply fluid dynamics, you predict that there's an infinite amount of viscous heating going on in some system that has no atoms in it. And so you get an arbitrarily large error by ignoring this problem. Okay. Now, fundamentally, again, there's nothing wrong. I mean, we know a perfectly valid theory for the dilute corona. It's just ordinary Boltzmann kinetics in the ballistic limit. But what we somehow have to do is we have to marry that dilute limit to the dense limit where it's fluid dynamic. And now, in principle, you could have, and in the heavy ion community, we actually do that sort of thing, that we indeed combine a fluid dynamic description for the center to a kinetic description of the corona. But the matching is always very tricky. You have to have some kind of interface that allows an atom to jump out of the fluid and into the kinetics. And to do that right is actually not easy and numerically cumbersome. And so for the present purpose, I found what I think is a simpler solution, which is to take a generalized hydrodynamic description where I not only propagate the strictly conserved charges, but also some non-conserved charges. That's always legal. You can always do that. Propagate some quantities that are not strictly hydrodynamic, and then relax to just local hydrodynamics on some very short time scale, and then you're not making a mistake. You're just putting in too much work. And so the extra non-conserved degrees of freedom I propagate are degrees of freedom that are conserved in the ballistic expansion. So I propagate, for example, the Cartesian components of the energy density, because without collisions, they can't change. So in a purely ballistic expansion, these would be conserved, but in a hydrodynamic expansion, they're not conserved. Okay? So these then do not obey an actual conservation law, they obey a relaxation law. And if relaxation is sufficiently fast, then it just goes to ordinary Navier-Stokes. But if relaxation is very slow, which is what happens in the corona, then I'm preserving the ballistic expansion of the system. So if you wish, it's just a method to smoothly extrapolate between ballistics and fluid dynamics. The theory will not be exactly right in the middle, but it has these two limits built in. And it actually works remarkably well. So this is a test that I did some years ago where the dots are, so this is a high temperature cloud. It's again this aspect ratio as a function of time. I let it expand. This is theory compared to theory. So the the dots are just a Boltzmann solver. So somebody actually solved the real Boltzmann equation in this high temperature limit, really as a sort of six-dimensional equation in phase space. And the lines are my hydrodynamic theory, which in principle is just Navier-Stokes, but has the ballistic limit built in. And this is a parameter-free comparison because I took as a viscosity exactly the viscosity that comes out of Chapman-Enskog. And it worked shockingly well. So this is a sort of consistency check that indeed, even though this is a fluid dynamic theory, it reproduces Boltzmann in the limit that it should. Okay. So now that I have this theory, I can analyze actual data. So this is a kind of second generation experiment that was performed by John Thomas at NC State. So he now has a cloud that's actually deformed in three directions. So all three oscillator frequencies are different. And he images it from two directions so that he can actually measure more than one aspect ratio. So he measures AX, AY, and AZ for this cloud. Okay. And that was done for various experimental reasons. So this then is as a function of the energy of the cloud, which is a proxy for its temperature. So eventually we'll take an equation of state and convert that to temperature. The aspect ratio measured at a fixed time. So in principle, you can watch the whole evolution of the cloud. But he at some point concluded that there was not so much information in that, there was more information in this energy evolution, so he just measured at a fixed time. So this is many, many measurements of the aspect ratio. In principle, the second issue is still this issue of having to unfold. And since I expected from these sort of many-body calculations that the dependence on density was maybe relatively smooth, I just went ahead and expanded that into a sort of virial expansion. So the leading term, the high temperature limit, is independent of density, but as you go to lower and lower temperature, we expect that there's actual density dependence. And I just, expanded that into a bunch of kind of virial coefficients for the viscosity. So that actually works remarkably well. These fits are only, so this point where I stop is the critical temperature where it goes superfluid, and we'll get to superfluidity in just a second. And what you see here is kind of the first order. This is the high temperature limit, the second and the third correction. And you see that it appears to converge, at least relative to the accuracy of the data. It seems to converge pretty quickly, and there's no need to include further coefficients. So when I do this, what I find is, number one, what I find kind of remarkable, I can now extract from experiment the viscosity in the high temperature limit. So at T much bigger than Tc, and it does indeed appear to scale as temperature to the 3½ with the coefficient that I can by now actually measure with pretty good accuracy, up to a few percent. This is maybe 2 or 3%. And so this coefficient is 0.265, and my kinetic theory prediction was 15 divided by 32 squared of pi. And you see that that nicely agrees within a few percent. And so there are really not that many systems where you have an actual quantum fluid and you can predict and measure and check its viscosity to that kind of accuracy. So that's where you can see that this is really a pretty clean system. So you can then extrapolate, we have an actual measurement that goes all the way down, actually beyond the critical temperature. I'll get to that in a second. So here, this is all in the normal phase. And here I already took the viscosity and normalized it to the entropy density of the system, measured by independent experiments. And as usual in these units where h bar and k Boltzmann are equal to 1. So this is where you have this kind of string theory limit of 1/4 pi. But here, and this is an arrow band that comes from my analysis. So you see that here the viscosity in the low temperature limit, it goes to about 1/2, not to 1/4 pi, with some uncertainties. Now, in this experiment, there's maybe ever so slightly a tendency for the viscosity to increase, but it was hard to say. And so we're clearly interested. This blue curve, by the way, is the high temperature limit. And this blue dash curve, I'll come to it in a second. It's some attempt to predict what happens at low temperature. Okay, but we are interested in what happens at low temperature. But at low temperature, now we really do need to include superfluidity. This advances. Here we go. So again, just a super brief summary. Am I on time? I have another 10 minutes or so, do I? Yeah. Okay. Okay, I'll keep going until somebody stops me. Okay, so now below TC, we're in the superfluid phase, so there is an additional hydrodynamic variable, which is the superfluid velocity. And so there's an additional hydrodynamic equation. So superfluid velocity is being accelerated essentially by gradients of chemical potential rather than gradients of pressure. And so now, my momentum density can be written in terms of a normal part and a superfluid part, and my density can be written in terms of a normal density and a superfluid density. Okay. So in this case, again, I can ask myself, so these are dissipative terms. In the superfluid phase, there's still only one shear viscosity, which is now kind of driven by gradients of the normal fluid velocity, but there are in total 4 bulk viscosities. So 2 of them appear in the stress tensor. This is this zeta 1 and zeta 2. Essentially, zeta 2 is what we think of as the normal bulk viscosity of the system. And 2 more appear in the equation of motion for the superfluid velocity. So there's a zeta 3 and a zeta 4. And one of the peculiar aspects of scale invariance in these non-relativistic systems is they don't actually all have to vanish. In principle, there's one bulk viscosity that can still be present even in the superfluid system, but it turns out to be hard to measure. So in principle, I know of a protocol that would measure it, but again, it truly does involve the acceleration of the superfluid in response to a difference between the normal and the superfluid velocities. So it can, at least in principle, be measured in the attenuation of sound and second sound in the superfluid phase, but in practice, it's not that easy to do, and we have not been able to do it yet. Okay. So what will we expect for the viscosity and the thermal conductivity in the superfluid phase? In principle, if you go to very low temperatures, there's again a kinetic description, because in the very low temperature phase, you have weakly coupled excitations that are just superfluid phonons, and I can build a kinetic theory out of that. The interaction between phonons is governed by some effective Lagrangian, and again, scale invariance is sufficiently powerful to completely constrain up to an overall parameter the nonlinearity in that effective interaction. So I actually do know from first principle the scattering amplitude between 2 phonons. So I do know what these vertices are. They have a known strength. The system is weakly coupled at low energy, which means that at low temperature, the phonon gas is a weakly coupled fluid, and it will have a large viscosity. So in principle, one actually predicts a relatively strong divergence of the viscosity as you lower the temperature. It goes as 1 over temperature to the 5. Okay. That effectively will make it hard to observe, because what it really means is that the mean free path of these phonons just grows very, very quickly. So in any kind of finite system, you'll very quickly have a situation where the phonon mean free path is bigger than the size of the system. So I'm actually not sure if with the systems that we have today, we can realistically observe this, but in principle, that is a prediction of kinetic theory. Similarly, one can predict the thermal conductivity of the system. That too will ultimately be a kind of complicated process, because for strictly linear quasiparticles, you would actually predict the thermal conductivity to vanish. So it completely comes from nonlinearities in the phonon dispersion relation. So again, in principle, we know what those are, but I'm not entirely sure if one can actually observe that in a relatively small system. Okay. So if you now want to do 2-fluid hydro, again, you need to know the equation of state sufficiently well. You need to know the superfluid density that actually is known from independent experiments. So this is the kind of cloud that we initialized, that this kind of looks Gaussian. It actually isn't quite Gaussian, because the equation of state is more complicated than just the high temperature limit. But at any finite temperature below TC, it'll have a superfluid core. And then, there's a kink here where the system becomes completely normal in the sort of dilute corona. Okay. So we take an initial condition like this, and we now propagate it forward in superfluid hydrodynamics. Initially, again, I thought that that might be kind of complicated to solve the full nonlinear superfluid hydro equations, but it turns out to be relatively straightforward, and that's because in the system, you're now accelerating both the normal and the superfluid, so there will be a normal velocity and the superfluid velocity. In principle, these could be quite different because one is accelerated by gradients of pressure and the other one is accelerated by gradients of chemical potential. But in practice, you start with a cloud that's initially isothermal, and so there's no difference between the acceleration seen by the normal and the superfluid. There's some viscous heating that will make it, not quite isothermal and effectively launch a sort of second sound wave into the system. But the amplitude of that wave is really quite small. You may not be able to read this. So this is ordinary velocity for different times. So this is this kind of Hubble flow. So this unit is 1, and this unit is 0.01. So the amplitude of the second sound wave, so the relative magnitude of the normal and the superfluid velocity is quite small. So you effectively can kind of treat this in perturbation theory, and it expands almost like an ideal normal fluid would. Okay. So when I do this, so this is a blow up of this plot that I showed earlier of measurements by the NC State group. This is now plotted not against energy, but as against a function of temperature, but this is a very small label where the critical temperature is precisely here. And in these expansion data, you actually do see a sort of kink where the aspect ratio trends up below TC, which would, intuitively mean that the viscosity must be dropping because the system expands even faster. And indeed, if I try hydrodynamic fit, so this, green curve is something like my best fit, that corresponds to a viscosity that actually is dropping fairly significantly below TC. Okay? So I find a roughly exponential drop of the viscosity below TC, so that half TC, the viscosity has dropped to, say, 30% or something. So what is interesting is that in principle, there are other ways that may be ultimately preferable to get at this question. And this is a schematic of an experiment that's being done. Very good, I can do that. This is a schematic of an experiment that's done at MIT in Zwierlein's group, where he takes a gas in what is essentially a box trap, a cylindrical thing with 2 end caps, and then he shakes the end caps to make sound modes. And in this system, I can now study viscosity and thermal conductivity by measuring sound attenuation. Okay. So this is a busy plot. He can measure the spectral response to, again, shaking his trap, and the width of the spectral response is effectively sound attenuation. And he can, in particular, inject that sound attenuation is indeed hydrodynamic, so that it scales as wave number squared. And at high temperature, it actually very cleanly scales as wave number squared. At low temperature, below TC, it scales approximately quadratic at low wave number, but then it looks more linear. So this is a sort of breakdown of fluid dynamics. It looks more linear at higher wave numbers. And so this is the diffusion constant or the damping constant for sound. That's a linear combination of viscosity and thermal conductivity. If you wish, it's 4/3 viscosity and 4/15 thermal conductivity. So in that experiment, you cannot directly deconvolute those two. You just measure that linear combination. But what is interesting, so at high temperature, he measures a sound attenuation that is indeed dropping in a way that's essentially predicted by the drop of viscosity seen earlier. But below TC, and this is a blow up, it doesn't seem to exponentially go down. It seems to be essentially constant. Okay? Right now, I don't exactly know where that discrepancy comes from. My only suspicion is that, again, these two experiments explore slightly different regimes of system size and wave number. But so right now, the hydrodynamics is consistent above TC, but not below TC. And there's yet another class of experiments where we're currently looking into this. So this is a linear response experiment that's continuing at NC State. That's, again, a box trap, but now not shaken, but we just have a traveling wave that runs through it. And I'm studying the hydrodynamic linear response to that traveling wave. So far, we've only used that at high temperature, where you can check the kinetic result for thermal conductivity. Again, so this is what kinetics would predicted, and we're within sort of 7 or 8% of that prediction. Okay. So just to summarize some final thoughts, again, we have a sort of program of trying to unfold the temperature and density dependence of these transport coefficients like viscosity and thermal conductivity. that seems to work nicely above TC, but there are some discrepancies below TC. And at some level, they must be related to breakdowns of hydrodynamics in at least some of these systems, that it's not truly superfluid hydro because the system is too small or too rapidly expanding, or you're probing it at frequencies that are too high. Ultimately, we would like to measure the really short time and short distance response to, for example, see these behaviors like 1/squared of omega predicted by the operator product expansion. And we would like to see more clearly, indeed, how we approach hydrodynamics, whether there is somehow, again, the sort of quasi-normal mode behavior that, for example, would be predicted by holographic models. Well, thank you so much, and sorry for going over time slightly.
So questions? So let me ask a question. So you were showing these Aslamazov-Larkin and Markey-Thompson corrections in the early part of your talk.
Can you say that again?
You're showing these Aslamazov-Larkin and Markey-Thompson corrections.
Yes, yes.
So there, I mean, I'm familiar with the results for the conductivity, and they're supposed to diverge as you approach TC. What are the analogous results for viscosity? Yeah.
So these diagrams, what exactly happens as you approach TC depends on precisely what you put into the fermion propagator. So for example, they could diverge if you put pair fluctuations in. In that particular calculation, the one that Ensign Serger did, I don't think that was done. So there is, a sort of pseudo gap developing, but there are no pair fluctuations. So I think if you did that, you would indeed predict some kind of divergence. Purely hydrodynamics with stochastic fluctuations would also predict a really, really mild divergence. But in any event, as you saw from the experiment, so currently neither one of these behaviors is seen. So there's one class of experiments that suggests that viscosity is just dropping, and there are these sound attenuation experiments that are actually pretty accurate. So if there was any kind of strong fluctuation-related phenomena, you would imagine that you would see a divergence, but right now you don't see anything. It seems to go through TC relatively smoothly. And in these expansion experiments where you expand out of a trap, you always have to sort of argument that, well, the region that's truly critical is just some kind of shell, and maybe that's so small that you don't see it. But that doesn't really apply to these kind of box trap experiments, because now the whole fluid, if you can keep it, the temperature sufficiently controlled, it's the whole fluid that's supposed to be critical. And now I plan to look at this more carefully because, again, coming from the heavy ion community, we're actually very strongly interested in seeing critical fluctuations in hydrodynamics. There's a whole program of observing that in the heavy ions. And so I plan to look more closely if we can make box traps where we keep the fluid very close to critical, and we really check that it has critical behavior. We look at, say, density fluctuations in the fluid, and we hopefully see that everything behaves correctly, and then look if we can see something interesting in the transport. That's the sort of program that we want to do.
I just have a simple, in general, in cold gases, besides the elastic interactions close to unitarity, there are three body losses. So you don't see any effect. I mean, in the experimental measurements, do you see they are playing an important role compared to the theory, or how you're removing those?
Can you say that? I missed the beginning.
Okay. So in most of the experiments close to the unitarity, in the unitarity regime, there are also three body losses, or in elastic terms, that the scattering length has also an imaginary part that modifies the dynamics. Are those important for your comparison, or how you do to remove them from when you compare with the experiment?
So the lifetimes in these experiments are actually really pretty good. So this whole, I don't know, there is an actual time scale on these plots that you saw. Actually, this isn't dimension as units. But this one had an actual expansion timescale on it, which was about 20 milliseconds. So over the 20 milliseconds, the three-body losses are not that large. And in this analysis, we tend to ignore it. There is a separate context where I actually tried to look at it, which is that this is the sort of system where, so roughly speaking, what we now see in the analysis is that, I tried to make this kind of virial expansion for the viscosity. And empirically, what I find, here it is. So empirically, I find that the viscosity in essentially the entirely regime can be described by just the first two terms, and the third one is really small. And this term, since this is two-body interactions, this term actually is three-body interactions in kinetic theory. So I at some point made an attempt to compute this in kinetic theory and got all confused as to how to correctly treat the three-body collisions in kinetic theory. But it's one of these problems. If I ever have enough time on my hand, I actually would like to figure this out, how to properly include the three-body collisions into the kinetics. But yeah, in the analysis right now, we're actually ignoring it. And our rough excuse is that the timescale of the expansion appears to be short enough that three-body losses are not that important.
I had a couple of questions. The first was, so you had this expansion setup. Could you go back to that? The one where you mixed up the Boltzmann equation for the stuff on the outside with the hydrodynamics of the stuff on the inside.
I was having trouble advancing the slides here. Yeah, so there was my sketch.
Yeah, exactly. So I'm a bit confused about what the setup is here. So is the fluid expanding?
Yes. So, well, in the actual experiment, the fluid sits in a harmonic trap. It's a laser field that makes the harmonic trap. And then the harmonic trap is just switched off. It starts to expand at this point.
So I guess what I'm confused about is, are these two components, this sort of free gas component and this dense liquid component, talking to each other, or are they just sort of spatially separated?
This is why I sort of fuzzed it out. There, of course, is not a sharp distinction. You can kind of roughly identify these regions by trying to estimate the mean free path. And loosely speaking, there is a region where the mean free path is just much smaller than all the gradients, and there's a region where the mean free path is now much bigger than all the gradients. But there is no sharp distinction. And in fact, since the fluid, it's being pushed by gradients and pressure, the fluid is actually accelerated more strongly than dilute corona, which is just the gas of particles with some thermal distribution. So the fluid is a sort of snowplow that runs into the dilute corona.
Okay, so they're coupled by that mechanism. Yes. Okay, thank you. Also had a sort of bigger picture question, which is, I remember 10 years ago when I last thought about this stuff, there was this big numerical task to compute certain quantities in the unitary Fermi gas, some dimensionless numbers that, people didn't know what they were. And I guess I'm trying to understand how your results sort of connect to those questions, because it seems as if you managed to get analytic predictions for a bunch of stuff.
Yeah, so we still care deep. I mean, the very first of these is this famous Birch parameter. So what is the chemical potential of the interacting system in units of the non-interacting one, which completely fixes the equation of state at zero temperature. That is now known both experimentally and numerically to maybe 3 or 4%. We actually care about that one deeply in nuclear physics because it's an important benchmark for doing the nuclear equation of state, because it so happens that the neutron-neutron scattering length is very large, and the real world happens to be close to that. So that is still being pursued. But then again, there are many other things. The gap, the critical temperature, these short distance form factors, the static structure factor, the dynamic structure factor. And if you wish, these coefficients that appear in transport is just one of these many things, these universal numbers about the unitary Fermi gas. But since they're real-time properties, they're harder. So the equation of state can be done numerically or it can be done experimentally to pretty good accuracy. But numerically in, quantum Monte Carlo, we still don't know how to do viscosity. There have been occasional attempts to do it, but it suffers from the usual problems of taking imaginary time Monte Carlo and having to continue to real time.
Okay, and so you're doing essentially some perturbation theory as a way of getting at these transport things that
well, and I'm also just analyzing experiments. So experimentally, they can of course be measured. Not all of them, not as many as we would like. As I say, we'd like to engineer something like linear response to a gravitational perturbation and so on. So we don't quite know yet how to do that. But in principle, experimentally, of course, they can all be measured. Some of them people can do analytically with sort of unjustified approximations, but it appears to work pretty well. Some of them can be done with quantum Monte Carlo, but not the transport. Thank you so much.